Our next speaker on stage is Oliver Michel. Did I get that right? Close enough? Okay. Who will present enabling passive measurement of Zoom performance in production networks. Oliver is a postdoc research associate at Princeton University. This is your second time presenting at NANOG. The first one was called Packet Level Network Analytics Without Compromises, which was at NANOG 73 in Denver in 2018. Welcome back to NANOG, Oliver. It's a pleasure to have you back.
All right, thank you very much for the introduction. So especially over the past couple of years, video conferencing has become an essential application across multiple industries with critical use cases in healthcare, enterprises, as well as in education. There's been a lot of interest in the research community with work on video codecs and rate adaptation algorithms, but also understanding the network's impact on video conferencing is also important to network operators. These applications are latency sensitive and bandwidth hungry, and network operators need to run and configure their networks in order to provide best possible quality of service to their users and best possible video conferencing performance to the customers. Now, measuring video conferencing applications from the network point of view is actually pretty complicated. And as a result, previous work, mostly and large-scale studies on this, mostly exclusively relied on the overall data rate of, for example, a flow. But unfortunately, we saw this is really insufficient to make any meaningful inferences about the traffic, let alone reason about cause or saying like why a particular phenomenon happened. So let's say, for example, we're able to isolate a Zoom UDP flow. The majority of Zoom is transported over UDP. And we look at the data rate over time and have this plot here. So now we see this sudden drop in the data rate, and we want to know what's going on, and especially whether this is in response to a network problem, so like congestion or packet loss. So it turns out this can actually be due to multiple issues, and none of them have anything to do with the network directly. So for example, in Zoom, over a single UDP flow, there's multiple participants and media streams being multiplexed. And this here could simply mean that in this case, this red participant is just leaving the meeting, right? Another thing could be a more subtle change. So for example, a change in meeting mode. This means when a participant's video is going essentially smaller, what Zoom calls gallery or thumbnail mode. And the pattern that you would see in the overall data would actually be the same. So the point is that we need to dig deeper to extract more meaningful metrics, like, for example, latency, jitter, loss in retransmissions, out-of-order packets, frame rate, frame sizes, media bit rate, and then most importantly, evaluate those metrics in conjunction with the overall meeting composition, meaning the number of participants that are currently in the meeting, when somebody is leaving or joining, and what types of media they're actually sharing in order to make more meaningful inferences and say whether the network is potentially a problem in a particular call. Now, network operators have massive amounts of video conferencing traffic from all of these different applications running through their networks, but getting these metrics from the traffic through passive measurement is actually pretty complicated. And the main reason for that is that these quality and performance metrics are usually not directly observable from the traffic. Now, there's some applications, including Zoom, that do provide some sort of QoS data through their application. So, for example, in Zoom, you have the statistics window in your Zoom client, but it's really only useful for small-scale or controlled experiments where you really have control over the end hosts and can perform end-to-end measurements. In general, we found that the operator's vantage point and also their capabilities in measuring performance of video conferencing have just not been very well explored in the past. So to summarize, our goal here is to measure and analyze the performance of video conferencing sessions in the wild. And that means using only passively collected traffic without any end host control, and in large-scale networks at tens of millions or hundreds of millions of packets per second even. So for this particular study, we chose Zoom for two reasons. A, it's like very widely used in general, and also the recommended form for video conferencing at the Princeton campus. But it's also particularly challenging since Zoom uses a completely proprietary and previously undocumented packet header format. Now, achieving this goal is actually pretty complex, and the main reason for that is that video conferencing itself is rather complex, way beyond traditional on-demand video streaming. For example, meeting participants can be interconnected through different topologies or architectures. So you can imagine like a direct peer-to-peer connection between meeting participants. But video streams can also be relayed through an intermediate server, so-called SFU or selective forwarding unit, that will receive a participant's media stream and then like send it with some adaptations, for example, due to device capabilities or congestion on a downlink link to the other participants. Also, the control traffic that would tell us how to interpret different header fields in the actual media traffic is usually encrypted, and so is the media itself. And last, there's a complex hierarchy within the network protocol, such there's not necessarily a direct and obvious mapping between a single packet that you capture on your wire to what meeting, for example, this packet belongs to. So in the context of Zoom, we're asking the following three questions. First, how do we reliably detect all Zoom traffic? Second, what is Zoom's packet format and what information can be extracted from those packets? And then last, how do we group packets belonging to the same meeting together to, for example, measure the latency within a meeting? So let's start with detecting Zoom traffic. So for the case where Zoom uses a server, this is actually relatively straightforward. Zoom publishes the list of IP addresses and port numbers that they use on the server side. And even though they use ephemeral port numbers on the client side, we can simply filter for the server-side addresses and port numbers. Now for peer-to-peer traffic, which is often happening when there's only two participants, this is quite a bit more complicated. However, what we observed is that before a direct peer-to-peer connection between two participants is established, we see an exchange of so-called STUN or session traversal utility for NAT packets right before the establishment of the peer-to-peer connection. Those packets go to UDP port 3478 on the server side at one of these published IP addresses of the servers and use an ephemeral port number on the client side. We then observe that this ephemeral port number, which makes sense because a hole needs to be punched through the firewall, is then later on used for the direct peer-to-peer connection. So in other words, simply by memorizing or by observing the STUN exchange, memorizing the client-side port number, and then with a configurable timeout filtering for that traffic, we can also detect direct peer-to-peer media connections between clients. Next, we need to understand the packet format. So right now, if you observe Zoom traffic through Wireshark, for example, you would see roughly the following. So after the UDP header, and UDP is used in the vast majority of cases, Wireshark would not be further able to analyze the packets or parse the packet format simply because it is unknown or has been unknown so far. So Zoom states that all of their traffic is encrypted, but we were naturally curious and were wondering if there are potentially any unencrypted parts in their packet headers. And if so, if we can find any patterns in those unencrypted parts of the packets that could potentially map to either their own proprietary protocols or potentially to a widely used protocol like RTP, for example. So in order to find that out, we did some graphical entropy analysis of the packet payload. So we looked at basically the entire payload after the UDP header, and we plotted the byte values or the binary values over the sequence of packets over time. So then we generated really hundreds of these plots automatically, where usually on the x-axis we have either the packet index or a timestamp, and on the y-axis we have the binary value of that respective slice. So here you see, for example, 1 byte or 2 bytes being extracted, and we experimented a lot with the different slices that we extract from the payload. A real-world example of this is actually this here. So here we extracted 4 bytes. In other words, so as a result, the value range on the y-axis is 0 to 2 to the power of 32 minus 1, and on the x-axis you see the time here. So through that, we were able to see 3 distinctive patterns. The first one is really completely randomly distributed byte values showing maximum entropy, and this corresponds to either encrypted traffic or means that we hit the media payload directly. The second pattern that we saw were horizontal lines, so those correspond to identifiers. So think about a unique stream identifier, for example, or a bit field that might indicate, for example, what type of traffic it is, like what media type or something along those lines. And the third pattern that we saw were diagonal lines, and those correspond to sequence numbers or timestamps. Now, as you saw before, in reality, these plots look a lot more complicated, a lot more messy, with multiple lines wrapping around, overlapping each other, and so on. And I refer you to the paper for more details on that. So with this, we were actually able to do a lot more like detective work and then eventually find recurring patterns of these like byte value patterns, and also infer eventually the dependency between those. So starting at the UDP header, we were then able to really map out the full packet format that Zoom uses, which was previously unknown to the public. So the first header that we see is what we call the server SFU encapsulation, as it's only present in packets that go through a Zoom server. There's a type, in this case type 5 means that it's a media packet. There's a sequence number and also a direction indicator, even though this is also clear from the IP addresses. The second header that we see is what we call the media encapsulation header. So here we also see a type number that indicates the type of media that's being transported, or whether this is a feedback packet using RTCP, for example. So the media type would be video, audio, or screen sharing. There's a sequence number, timestamp, frame number, and also the number of packets that make up this particular frame. And then after that, at different offsets from this media encapsulation header, depending on the media type, we do see a almost used up to standard RTP, a real-time transport protocol header, using also a unique, at least unique within a meeting, synchronization source identifier, and also using a set of RTP header extensions. One of those extensions, for example, looks very much like a frame type indicator, as would be used in scalable video coding. So we believe Zoom uses that as well, but we did not actually further investigate that part. And then only after that, at least for video, we do see a H.264 network abstraction layer unit header. And then only after that, we see the media, which is then really encrypted. So to document all of this, we wrote a custom Wireshark plugin, which is available as part of the artifacts of our paper, which you can download today and inspect very easily your own Zoom traffic right away. So now we have all of this knowledge of the different header fields, how Zoom roughly operates. But for some of the metrics we want to get to, especially latency measurements, and also to make more meeting-wide inferences, we need to know which of these individual streams actually belong together and form a single meeting. So we developed an algorithm for that. The details are somewhat complex and are in the paper, so I refer you to that. But at a high level, we follow a two-step approach there. In the first step, we look for what we call duplicate streams. So this happens when we see the same media signal, essentially, being sent from a participant on our campus through our monitor to the Zoom server, and then this very same stream is actually being relayed by the Zoom server back to the client on our campus. Zoom does not translate sequence numbers, does not translate timestamps or anything like that. So it's relatively straightforward to see these, find out these duplicate streams. Then we developed a heuristic in a second step using association with timing information, IP addresses, port numbers, and so on, to really group those unique streams that we have now together into a meeting. And this allows us now to compare the RTP sequence numbers that we see on the outgoing and incoming legs to compute the round trip time to the Zoom server from our monitoring point on for every single packet that we see. This is hundreds of packets per second in some cases for a single call. So taking together all of this knowledge of detecting Zoom, the packet format, and also the grouping heuristic, we can actually draw a pretty detailed map of every Zoom meeting that's going on in our campus. So take, for example, a meeting with two participants, participant 1 in red, participant 2 in blue, and participant 1 here shares their audio and video at some point during the meeting, and participant 2 shares their audio, video, and their screen. So at the level of UDP flows, we can say exactly when a participant is joining or leaving a meeting. And then going further at the level of RTP media streams, we can exactly say when a given participant is actually sharing a type of media. So here in this example, for example, you can see that during the time where participant 2 in blue shares their screen, participant 1 muted their audio. Going even further then, we found out that Zoom uses different payload types to encode whether a client is currently emitting sound or not, at least on the audio stream. So as a result, we can very specifically say, like down to each frame or each audio sample in this case, whether a given participant is currently speaking or not. And this is all part of the unencrypted parts of the headers. Still, the main goal of this work was actually to analyze these performance metrics over time. So just the knowledge of the protocols and all of that is not the whole story. But with this, where previously it was only possible to get the overall flow rate, we can now compute more detailed metrics like the media bit rate, as we know exactly what packets belongs to what media, frame rates, individual frame sizes, the latency to the server, the RTP jitter, and then like loss-related statistics and retransmissions, as well as out-of-order deliveries. All of these metrics, these more detailed metrics, require this like detailed knowledge that we obtained in the previous steps about the headers, for example. And actually 3 of these metrics are also programmatically available through the Zoom SDK. And as a result, we were able to validate our estimation techniques using the ground truth as provided by Zoom. So let's start with frame rate. So I'm going to go through these 3 now. So we conducted a couple of controlled experiments where we instrumented a Zoom client using the SDK. And in this modified client, this actually emits and receives the exact same type of packets. We were able, whenever we get a QoS metric update, to log that particular the data point and then compare it with our measurement. So here in this plot, you see in one controlled experiment where we actually injected cross-traffic twice over the course of the experiment. You see the blue line is our network measurement using like the per packet data, and the red dots is the data that Zoom provides. And as you can see, our frame rate measurement matches the Zoom provided data actually pretty much exactly. The main difference here is that we provide many more data samples. So Zoom updates this metric once every second. And we can provide a new calculated frame rate once for every frame. So this can be up to like 28 or 30 times per second or so. Next, we looked at the latency to the Zoom server. So we did this, as I said before, by matching the RTP sequence numbers and then like measuring the time in between. And here we can see that our latency measurements also, generally speaking, do match the Zoom provided data. However, it appears like that Zoom uses pretty like long term and like pretty aggressive smoothing in the way they report the data. Also, we get a sample, a latency reading for every single packet. So this can be for a single meeting, can be hundreds of times per second, depending on the number of participants and flows, whereas Zoom really only provides a single measurement every 5 seconds. And also it appears that the data is a little delayed overall. Then we looked at jitter. So we compute jitter the way as it's recommended by the RTP RFC. And here we actually see a pretty stark discrepancy compared to the data that Zoom provides. So Zoom, in this case, reported jitter pretty much close to 0 almost through the entire experiment. And actually, these 2 plots belong to stem from the exact same experiment. So you see on the upper graph the pretty significant latency variation. That was really the case due to the injected traffic and was also reported up to some degree, even though using smoothing by Zoom. So at the bottom line, it seems rather unlikely that the jitter would really like stay completely constant throughout this experiment. So then to put our tools to work, we performed a larger measurement study on our campus. So at Princeton, we have all routers that connect to the internet in all directions, equipped with taps that mirror all of the traffic entering or leaving our campus. And there's roughly like 10,000 or so people on our campus to get you an idea of the size. And this traffic is being forwarded to a P4 programmable switch that runs at 3.2 terabits per second and like does then all of the Zoom filtering for both server as well as peer-to-peer traffic at line rate. So we wrote this program for the data plane. Only the actual Zoom traffic is then further being forwarded to a analytics server for storage, live analytics, as well as retrospective queries. And doing this roughly reduces the amount of packets that we have to analyze then in software, which is relatively costly, of course, by 1 to 2 orders of magnitude, depending on the time of the day. So, and a summary for this trace, this trace covers roughly 12 hours, was collected after the pandemic in May 2022. So most of the instruction on our campus at that time was already back in person. The trace contains 1.8 billion Zoom packets, roughly 43,000 per second. Average data rate is 222 megabits per second, and this trace contains roughly 59,000 unique Zoom RTP media sessions. Over the course of the day, the overall bit rate broken down by media type, so here you see in blue video and then audio and screen share, looks like this. So kind of as expected, video makes up the vast majority of traffic volume, followed by audio and then followed by screen sharing. You do see a peak roughly at the beginning of each hour, presumably when meetings start, and then like people probably turn off their video at some point. Also, you can see a dip during lunchtime. So this is this is Eastern local time here on our campus during a weekday. And then you also see a pretty significant downwards trend there toward the end of the workday around 5 or 6 p.m. For this paper, we're really only scratching the surface of kind of the different types of analyses, especially like in terms of a single meeting, what is possible. But to give you a glimpse of the data and what is actually possible during using this, I'm going to talk about like 3 different metrics I'm going to show you over this entire trace, which is the number of participants per meeting, the round-trip time to the Zoom server, as well as the video frame rate. So first, the number of participants. So we use this grouping heuristic that I was talking about earlier. Using this, we were able to identify 803 distinct meetings over the course of those 12 hours. And as you can see in this cumulative distribution function here on the right side, roughly 50% of the meetings that go on in our campus have at most 2 participants. You see roughly 5% or so of meetings with only a maximum of 1 participant. So this is presumably when somebody joins a room and then nobody else joins. And then roughly 90% of the meetings have at most 10 participants. Then the latency. So latency, as I said before, we do measure by matching the RTP sequence numbers, and over the entire trace, this provided us with a little over 30 million latency samples to 521 distinct Zoom server IP addresses. And we know from both our measurements as well as the data that we have through our Zoom Enterprise account that roughly 80% of our meetings on the campus are connected to data centers in the New York City metro area. Again, we are located in central New Jersey. And roughly 20% are connected to servers on the US West Coast in San Jose. And even also here in this latency curve, you can see exactly this. So like this probability mass roughly corresponds to the calls that are being connected to servers in California. And this here would be New York City. Next, we look at frame rate. So frame rate is particularly interesting because this is something that's very tangible to the user, and where you even small and short-term variations can have a direct visible impact on the video quality. So we know that Zoom, under perfect conditions, without any loss or anything, aims at encoding video at roughly 28 frames per second, with some variability due to the software encoding that they do. But actually here in this CDF, we see that roughly 75% of the samples that we have of our data points show a frame rate of less than 20 frames per second. So the question is the network really that bad in 75% of the cases? So here the answer is it's not, actually. What we also observed is that whenever Zoom reduces the resolution of the image, it will also directly cut the frame rate in half. So we'll go from 28 frames to 14 frames a second. And this actually shows that a lot of video is transported in this thumbnail mode, and this is not necessarily a network problem. Whenever the frame rate significantly drops below 14 or so, this is more of an indicator that something in the network is going on. But the bottom line here is that you need to look at all of these statistics and metrics in conjunction to make these calls. So frame rate alone is clearly not sufficient. Interestingly, for screen sharing, this curve looks somewhat different. So here you see that even roughly 15% or so of our samples show a frame rate of 0, really indicating that Zoom uses a more content-adaptive encoding strategy for screen sharing. So for example, in a presentation like this, when the slide does not advance, it looks like Zoom will also not encode and send over the network a new updated video frame. So in conclusion, our work enables the future research and performance measurement on Zoom by demystifying its network protocol and operation, and also showing how to extract useful performance and quality-related metrics from exclusively passively collected measurements from within the network. Currently, we're working on even better QoE metrics, for example, a model to estimate the likelihood that a particular segment in the video stalled or froze. We're looking at bringing these measurement techniques into programmable switches to enable continuous, passive, and real-time monitoring of video quality performance. And we're also looking at ways to offload some of the selective forwarding unit functionality to programmable switches to reduce overall latency and operational cost of video conferencing infrastructure. The paper artifacts are all available online at this URL. This includes a pretty wide suite of analysis tools, notebooks for visualization, this Wireshark plugin that you saw a couple of times, as well as the P4 capture program that we deployed on our campus production network. I encourage you to check out the paper, which is available at the ACM Digital Library. It was published in last year's Internet Measurement Conference. And with that, I'm happy to take any questions.
Hi there, thanks for the presentation. John Christoph from NetScout. I'm actually quite struck by your work. I think it's incredibly good. This is what startups are made of, to be honest. Although maybe you're at the mercy of what Zoom might do. Have you looked at quantifying perhaps maybe differences in the sources and destinations to make evaluations of like the performance or latency, that kind of stuff of, you know, a network maybe worse or better because of, you know, the network they're at or that sort of thing. So other than just the overall meeting metrics, but individual participants within the meeting.
Right. Yeah. So I mean, basically, a lot of these like latency measurements that we have here really go to just to our monitoring point, right, and then to the server. That being said, there's always a TCP control connection, for example, that where we can measure the latency in both directions, right? So we get like by matching the ACK numbers, we get the latency in both to the Zoom server as well as within our campus. So we can, for example, pinpoint a wireless access point that a client might be connected to that is not bad, that is, you know, is overloaded. Also, all the individual media streams, so for all of the other metrics, so like the frame rate and like jitter and so on, this will be per participant, right? So it's not like we need to know what participants belong together. Still, the individual frames go to a single, like originate at a single or go to a single participant. So you can really like pinpoint, for example, individual access points that might be faulty, parts of your network, or even individual clients that experience issues.
Yeah, very good. Thanks again.
Hi, Tony Tauber, Comcast. It's really great work, I agree. How much, maybe you mentioned this, but how much, if at any, have you interacted with Zoom at all to, you know, share the results and see what they have to say?
Yeah, actually, so I mean, like after we did all of this, we did reach out to our Zoom contact, or like basically our account manager, since we have an enterprise account. And there were still a couple of things where we're not entirely sure, especially around the use of like forward error correction and things like that. And actually, it turns out that they connected us with some engineers. And we were correct with those things in most cases, but those were like more out of their curiosity, not really had an impact on the measurement techniques. The discrepancy in jitter is something we're still currently working with them on resolving. That being said, yeah, so we do have a relationship with them and kind of like working together.
That's nice. Thanks.
Mm-hmm. All right. Thank you very much. Thank you.